Hello, everyone. Back again with Chapter 14, Section 4, introducing you to some other higher order functions from the purrr package. Notice there's a typo. So we actually saw keep in the last screencast, but let's go ahead and introduce it formally along with its close relative discard. So keep works a lot like dplyr's filter does on a data frame, but filter chooses rows of a data frame based on a given condition, and keep chooses the elements of the input list or vector.x based on some condition that it calls .p. .p is going to be a function that returns true or false, and you keep stuff when the function returns true. Sorry for the dog. So a simple example is to take your .x to be, say, the whole numbers from 1 to 20, and your plan is to keep the ones that are one more than a multiple of 3. So you're starting off with a vector. Keep is going to figure out that you want to return a vector, but just the numbers that are one more than a multiple of 3. And the way it works that is with the .p function. And so this is our shortcut for where the function of x is x mod 3 equal to 1. So let's see if it keeps what we want. Indeed, it does. On the other hand, suppose you start with a data frame, like in 111 survey, and you pipe that in as the .x argument to keep, where the .p argument is the is.factor function that returns true when a vector is a factor and false otherwise. Then in this case, keep is going to figure out that since you started with a data frame, you would like to return a data frame. So if I were to just run these first couple of lines here, then out in the console, I get this data frame where only the factors are kept. I still have my 71 rows, but only the factor columns are kept. Now, the purrr discard function is really just a rewrite of keep. It's equivalent to keep where the .p is not the condition. So, for example, if I have the vector of numbers from 1 to 20, and I want to throw out the ones that are one more than a multiple of 3, then I would use discard with my .p being that same function. So now I'm going to throw out something whenever the .p returns true on it. Let's see if that's working. Yes, it is. Or similarly, I could discard the factors in M111 survey. Here I'll just run this and show the structure in the console. And so notice the factors are all gone. We've only got our numerical variables. So those are pretty simple higher order functions. Let's work on a very interesting one called reduce. So the idea of reduce is that it has two, the first two of its parameters are a .x. So again, that's going to be a vector or a list type of object, some iterable that can be gone through. And it has a .f argument that's going to be a function. And that .f does need to be able to take at least 2 inputs. And what reduce does is the following. It starts by applying the .f to the first and the second elements of .x, and it gives some result. And then it heads back up to its .x, and it takes that result and element 3 of dot x and combines them using the dot f, getting another result. And then reduce heads back up to the dot x, and it's got its previous result. It takes the fourth element of dot x, combines it using the dot f, getting yet another result. And it keeps on taking that result back to the dot x vector, grabbing the next unused item from the dot x vector, combining it with the old result to get that new result, until all of the elements of dot x have been exhausted, gone through. And then it returns the final result that the dot f produced. So as an example, first of all, why don't I see if I can get the dog away from the little paper bag that it's chewing up. Okay, back with you. Say you want to add up the elements of vec here. Let's teach this to the global environment. Then, of course, you could use the sum function, and they add up to 14. And that works because sum has been written so that it can apply to arbitrarily many arguments, and it just takes them and adds them all up. But what if addition in R could only be done to two numbers at a time? Like, what if sum could only take two arguments? How then could you sum up a vector that has more than two elements? Well, just thinking about it logically, what you could do if you were given vec up here is that you could start off with the 3 and the 1 and add them, and you get get 4. And then you take that 4 and you add on this 4 in vec to it and get 8. And then you take that 8 and you add on the 6 in vec to that and get 14. And now you've gone through the vec, so you return 14. That's exactly what the reduce function is actually doing. So let's check that out. We take vec, pipe it in as the dot x argument to reduce, and our dot f is the sum function. Let's see if we get 14. Indeed we do. So I think by now you might see why reduce gets its name. You know, it's given a dot x argument that could have many, many elements. But step by step, it reduces the dot x to just one value. So a very common application of reduce is, correct that, very common application of reduce is to take an operation that maybe has already been written for you or that you've written before that is only defined on two items. And you can use reduce to extend it to operate on any number of items. So consider there's actually a function called intersect in R that will literally intersect any two vectors that you give it. So if I put vec1 here in my global environment and vec2, I just look at those two vectors and I see that they have 4 in common and 6 in common. I think that's it. Let's see if intersect of vec1, vec2 will give us the 4 and the 6. Yes, it does. Very nice. But a sad fact about intersect is that you cannot intersect more than two vectors at once. Like if I were to try intersect of vec1, vec2, and this third vector, 4, 7, 9, I just get this error. The third argument is unused. It just isn't in the programming for intersect. But with reduce, it's no problem. You can intersect as many vectors as you like, but you need to store them in an iterable, so why not store them in a list? So let's say that I've got these 4 vectors here, 4 vectors of names. And I just make a list out of them. I call it LST. And then I pipe LST in to reduce, where the .f function is the intersect. And it's fine at finding the intersection of all four of those character vectors. So far, we have been using as our .f some functions that are predefined for us in R, but you are totally okay to write your own function to use as the .f. Just make sure that it's able to operate on two arguments, because reduce is going to take as the first argument of the .f function whatever has been accumulated so far, and the second argument it's going to take as the current value out of the .x that it's going to combine with what has been accumulated. So just to illustrate how that would happen if you wanted to write your own special .f function, let's write our own reduce summation function. And as we do it, I want to also throw in a little bit of extra programming so that when the function runs, it shows the user the reduction process as it's happening. So consider this function mySummer, which I will now stick into the global environment. There it is. So it's a function of two parameters, ac and cur. Ac is short for accumulated, and cur is short for current. And first of all, it cats out, so far I have ac. And then it cats out, but just now I was given cur to add in. And then it returns the sum of ac and cur. So if we type in 1, 2, 3, 4 to reduce where the .f is mySummer, then we should get 1 plus 2 plus 3 plus 4. Let's see if we do. We do, look at the 10 at the bottom, but along the way, we've got the process. It started off with 1, headed to the second element of the .x, added that in. Now its accumulation is 3, heads to the third element, which was a 3, added it in. Now it's accumulated as 6, headed to the last element of the .x, added it in, and it needed to stop. So that's good practice if you are writing your own .f function for use by reduce. Suggest that the names for the parameters should remind you of their roles in the reduction process. I would like to point out that reduce can also take an argument, a third argument, called .init. And when you give this argument a value, then the reduction operation does not start with the first element of .x. It actually starts with init as what is quote-unquote accumulated and goes to the first element of .x and then continues in the regular way. So if I try the same function call except adding in init equals 100, you can see this at work. See, it starts out with 100, then heads to the first element of the .x vector, and so on, ending up with a sum of 110. If you want to see sort of a more realistic example of reduction at work, you can consult the textbook. There's a rather extended example where you use reduce to build truth tables in propositional calculus. So if you're a math type person and maybe you've had discrete math and would like to see that at work, do feel free to study the example. Reduction functions are just all over the place in more pure functional programming languages, such as, for example, Haskell. Even the very simplest operations tend to be accomplished with them. So getting the logic of reduce down is really valuable for extending your programming abilities in the future. That's all for now. See you next time, probably with Chapter 15.